Algebra 1, Chapter 7, Section 7, Exponential Growth and Decay. Let's do a quick review. Match each situation in column A with what it models in column B. A person begins with 100 and earns $2 each day. Well, your constant is 100, and what's changing is the $2. So you're going to start with 100, and what changes is 2x. The second one, a person begins with $2 and earns $100 each day. So again, your constant is your $2, and your 100 multiplies by the number of days. So that goes here. And last, a person begins with 100, but each day the money doubles. Well, money doubles is an exponential gain, so that goes here. Our vocabulary for this section is compound interest. Compound interest is interest earned on both the principal and on any interest the account has already earned that remains in the account. So the amount of money deposited in the account is the principal. The amount of money earned on an investment only on the original investment, is the simple interest. But the interest earned on both the principal and the interest left in the account is called compound interest. So let's use the situation below, and we're going to identify the principal, the interest rate, time in years, and balance. So Susanna deposits $1,200 in a bank account. That's the original amount she puts in, so that's your principal. Now the bank account is paying 1.25%. That's your interest rate. And it's compounded annually for 5 years. Well, 5 years is the time in years. At which point, after the 5 years, the account holds $1,276.90. So what is exponential growth? Well, a quantity is growing exponentially if it increases by the same percent in each unit of time. This is a model of exponential growth. Y equals, sometimes you'll see f of x, equals A is the initial amount put in, times B is the growth factor raised to the x. So y equals A times B raised to the x is the exponential growth model. Here is a graph of exponential growth. Y equals A times B to the x. Now in this case, B has to be greater than 1. And as you can see, it's an increasing graph. A quantity is decreasing exponentially if it decreases by the same percent in each unit of time. In that case, it's called exponential decay. Notice that the formula for exponential decay is the same as exponential growth, but there is one difference. In exponential growth, the b had to be greater than 1. In exponential decay, the b has to be between 0 and 1. So it's going to be less than 1, but it's still going to be positive. As you can see, this is a graph of exponential decay. The graph is going down. Again, it never actually crosses the x-axis. As it decreases, it gets closer and closer to where y equals 0. Here's a review of what we've been talking about. We're looking at the function y equals a times b to the x. A is going to be greater than 0. When b is greater than 0, it models exponential growth, which means our graph looks like this. It increases. Same function, y equals a times b to the x. A is still greater than 0, but in the case where b is between 0 and 1, it shows exponential decay. So the graph is decreasing. In the case where the graph is increasing, the y value starts out close to 0 and increases with typically with time. Typically that's what x represents. In decay, the y value starts out quite high, but over time, over our x value, it comes increasingly close to 0. Here we have two functions. The first function, your b value, is greater than 1, so this is growth. In the second example, your b value is less than 1, but still greater than 0, so this is decay. Based on what we just talked about, could you circle the numbers that could be growth factors? And then in the next area, circle the numbers that could be decay factors? Take a moment, stop the video, try that out, and then check your answers with me when you get done. Remembering that growth factors are when they're greater than 1, our growth factors would be 3, 1.05. Remembering that decay factors are when they're between 0 and 1, that's 85%, 1/2, and 0.93. Once again, when B is greater than 1, it's a growth factor. When B is between 0 and 1, it's a decay factor. Let's take a look at what this looks like in a story problem. So in 1985, there were 25 cell phone subscribers in a small town. The number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were in the small town in 1994? So the 285 was our initial amount. The 1.75 is our growth factor. It increased 75%. At 100% plus 75% each time is our growth factor. This is our exponent is 9. And our new population, well, when we multiply this out, we're going to see it's 43,872. That's our new population. Using the previous problem, let's fill in each blank to make a true statement. In 1 year, there are 12 months. So in X years, there's going to be 12 times X months. The yearly growth factor of cell phone subscribers is 1.75. Now, as we just discussed earlier, it starts out at 100 because that's the total number they have, and it increases 75% each time. 1.75 raised to the X represents the yearly increase of cell phone subscriptions, where X is the number of years. So the expression that we would use to find the monthly increase in cell phones would be 1.75 times 1 to the 12th. If M represents the number of months, write an expression that represents the equivalent monthly cell phone subscriptions increase. It increases by 1.05 to the M. And of course, that is this value increased by the monthly cell phone subscriptions. Here's a formula for compound interest. A is your balance, P is your principal, which is the initial deposit, R is the annual interest rate. This must be expressed as a decimal. N is the number of times interest is compounded per year. It's in both places here. And then T is the time in years. Here's a story problem that we're going to use to solve an example of compound interest. Take a moment, read through this, and then go on to the next slide. And what is our principal? Well, our principal is the initial amount they put in. So our principal is the $2,000. Our rate is the annual interest, where as a decimal, their annual interest was at 4.5%, but as a decimal, that is 0.045. N is the number of compounding periods per year. So the number of times it's compounded per year is 12 because it's compounded monthly. And our time is 18 years. So we're going to substitute the values in the formula. So A is going to equal our principal, our $2,000, times 1 plus our interest rate as a decimal over the number of times it's compounded per year raised to the value of our N times the number of years, our time. Now N times T becomes 216. So 2,000 times 1 plus 0.45 divided by 12, 0.045 divided by 12 raised to 216 equals approximately $4,489.01. Please take a moment and read through this story problem about exponential decay. Okay, so between sea level and 5,000 m, the atmospheric pressure will decrease 5,000 divided by the 1,000, or a total of 5 times. So we're going to write a simple equation to find the atmospheric pressure at 5,000 m. Our initial pressure amount is this 101. We're going to multiply it by 1 minus 0.115. Now, do you know where I got that 0.115? Yes, it's this percentage point right here. And how many times does the number decrease? Well, we found out here that it decreases 5 times. Using order of operations, we need to do what's inside the parenthesis first. So 101 is multiplied by 0.885 raised to the fifth power. We're going to raise 0.885 to the fifth power first and then multiply it by 101. And we're going to get 54 point something. Of course, that rounds to 55 kilopax.